In this video, let's take a look at a one-sample hypothesis test for the mean when the variance is unknown and we're using a two-tailed test. In this example, we have historical information that the average time to complete an accounting audit is 264 minutes. A new checklist has been instituted within the organization, and we want to test whether the average time has changed using an alpha value of 0.05. So here, since we're testing to see if the value has changed, it could have increased or it could have decreased. This is how we know it's a two-tailed test. We have a sample of 15 audits that show an average of 258 minutes and a standard deviation of 8.38. Given this information, we know we're looking at a sample, which is also how we realize that this is a variance unknown example. Since we're using sample information, we're assuming that the variance is unknown. We would consider it variance known if we had population data. So while we do have actual numbers and data, it's from a sample. So that can be a little bit confusing sometimes because we can calculate the standard deviation. So we know it, however, it's considered unknown because it's coming from a sample. So given that we're testing the mean and it's a two-tailed test, we're going to set up our null hypothesis that the mean is equal to mu naught. And our alternative hypothesis is that the mean is not equal to mu naught. Our alpha value is 0.05. Our mu naught, we know, is 264 because that's what we're testing. And our x bar, which we calculated from our data, is 258. We also know S, which is our sample standard deviation, is 8.38, and our sample size for N was 15. Our degrees of freedom, since we have a sample, is going to be our sample size of 15 minus 1. Then for our t-table, we can calculate our t-test statistic. We're going to use the t.inverse.2t using our alpha value of 0.05 from cell B19 and our degrees of freedom, which was 14, from cell B24. So our positive t-value is 2.1448. For the left-hand side of our distribution, we're going to use the same calculation, but now it's negative to get the left-hand side. Our t calculation will be our x bar value from cell B21 minus our mu naught from cell B20 divided by our sample standard deviation from cell B22 divided by the square root of our sample size from cell B23. That gives us a value of negative 2.773. So we can come up with our conclusion then using logic. Let's take a look before we do that at how it falls though. Our t-value is negative 2.1448 and positive 2.1448. Our t calculation is to the left of our negative t-table, so we should expect to reject our null hypothesis. We can set this up with our logic within Excel so that we're looking to see if the value falls within the main portion of the distribution, we should fail to reject the null hypothesis. So we have if it's B27, which is our t calculation, is greater than B26, which is our negative t-value, and B27 is less than our positive t-value, which means it falls in this region, we're going to fail to reject the null hypothesis. Otherwise, we're going to reject the null hypothesis. So we get the correct conclusion that we're going to reject the null hypothesis based on where our value falls. So we can also calculate our p-value to understand our level of confidence with our calculation. To do this, we're going to use the t.dist dot 2t, since it's two-tailed function, we'll take the absolute value of B27, which was our t calculation, and then B24, which is our degrees of freedom, which was 14. We're using the two-tailed since it's a two-tailed test, and that gives us a p-value of 0.0150. This value is considerably less than our alpha value of 0.05, so we're very confident within our conclusion to reject the null hypothesis.